Good, okay. Addition rules for probability. Before I get started into this one, let's kind of just remember some rules of probability that we talked about. Remember that in probability, sometimes the hardest thing is figuring out your sample space, all the possible outcomes that could happen. Now, in the last class, we made it pretty easy. It was like a coin flip, or it was dice. Maybe it was 2 dice, but it was finite. It was easy to find. We learned about classical probability. We learned about experimental probability. If something has a classical probability aspect to it, then as the experiment gets larger and larger and larger, what's going to happen? Think about it. What's it going to start getting close to?
Actual probability.
Exactly, the classical. As the experiment goes up, the closer it's going to match to that classical probability. I.e., if I flip a coin right now and get heads, and that's the only thing I know, then I think the odds of getting heads is 100%. But if I do that 100 times, 1,000 times, 1,000,000 times, it's going to get closer and closer to that 50-50 that we know it should be. Okay? Hardest part sometimes is figuring out sometimes the outcome space. Okay? The total outcomes. And then when you got to figure out what do we want to see. And remember, I was trying to be and it's very tough for me still. We still want to kind of figure out the top number. The F number is usually going to be, what do we want to see? I don't like saying the word favorable results, because if you're studying cancer and deaths, you don't want to say that's a favorable result. So we kind of look at it as what are we looking for? If I'm looking at the probability of rolling a 5, okay, on a 6-sided dice, then I know that the outcome I want is a 5. But how many ways can that happen? 1 way out of 6. Make sense so far? Okay. So how this is going to work today is most probabilities kind of don't work this way. Okay, we need to go back over some rules though real quick, because they are important. Recall, for any event E, the probability of that event happening will always be between 0 and 1. Okay, like the probability of me getting a 6 whenever I flip a coin. That makes no sense. There's no way for that to happen. That would be a probability of 0. But the probability of getting a heads or tails, one or the other, is 100%, because I'm going to get one or the other. Okay? Now, in the real world, things are going to approach 0, and things are going to approach 1. Okay? Because even the sun coming up tomorrow, the probability of that is not 100%. But it's so close to 100%, we just consider it 100%. Okay? So for any sample space, S, the probability of having something in that sample space is 1. It's literally saying if my sample space, okay, is heads or tails, and the probability of getting a heads or tails, that's 1, right? Makes sense. And then the empty set. Okay, remember if you took me in intermediate algebra, you learned about that symbol. That's called the null set. The probability of the something happening when there is nothing in there is obviously 0. And that's really when there's no possible way for that thing to happen. Remember, heads or tails getting a 6. It's not even in there. It can't do that. That's not a thing. So here we go. 0 cannot occur. Probability 1 will occur. This needs to be something you kind of remember always in the back of your head. Because even when we move beyond chapter 4, probabilities are everywhere in there running in the background, especially when we start getting into normal distribution. Everything we do in statistics is basically a probability. When I take a sampling of people, and then I say that they're 1 standard deviation, I'm not going to give you the number right now because there might still be somebody taking the test, but I know within 1 standard deviation, that's a number. That's basically kind of a probability going, I believe that there's roughly this amount of people within 1 standard deviation. That's the probability of that being that way. That kind of help y'all out a little bit? Okay. So, definition. Complement, not compliment. Not you have pretty eyes. Okay. It means the opposite. You have ugly eyes. No, I'm just joking. No, complement of an event E denoted E with a superscript C, or sometimes you may see it written in some stats books, even sometimes by me by accident. You may see it as E prime. Okay, that's what that little thing means. It means E prime. It just means it's a set of all outcomes in the sample space that are not E. Okay? Before I show you an example, it makes sense if I say it this way. What is the probability of me, we're going to think of a six-sided dice. What is the probability of me rolling a 5? 1 out of 6, exactly. Thank you. 1 out of 6. There's only one way to get a 5, right? Out of how many outcomes? The complement would be this. How many ways are there for me not to get a 5? 5 out of 6. Notice it's the remaining part. You have a probability here that says this is what I want. The complement is the everything else thing. Okay? Look at this one. The sample space S is all the numbers here. Okay? That's every single number I could see. That's why this would be my sample space right there. Now, the event I'm looking for right here, we can actually rewrite this in this way. The probability of E is that right there. I'm looking to get a 1, 3, or 6. What would be my probability for that? How many things am I looking to get? Count those in E. 3, right? Okay, very good. 3, what's the total? 6. So my probability is 1/2. You see how that's kind of working now? Now notice the complement. Okay, and I will be saying, I'm trying to think very hard not to put I in there. Well, the complement is also 3 out of 6, and it is also 1/2. But look, that's everything I don't want right there. I'm not looking for those guys. These are what I'm looking for because that's the sample space I'm wanting right there, right? That's the sample space of the E. That's the subset. Does that make sense? This should show you an inherent quality of these two, which says this. If you have a probability, the sum of the probabilities of event E and their complement will always equal to 1. Why is that?
There's 2 different percentages of a whole.
I like that. I like that. Think about it. If I say once again, what are the ways for me to roll get a 5 when rolling a dice? Well, 1 out of 6. What are the ways I can't? 5 out of 6. But when I take those two and put them together, what is the probability of me rolling what I want or the other thing? 6 out of 6. So it's got to be 1. Okay? Complement is going to help us out a lot, especially later on. Right now, I'm showing you complement because sometimes when you're looking for a probability, it's easier to find what you don't want to find and then take this complement than it is to find the thing you want. I'll show you shortly, okay? But this is going to become important later on, especially for you calculator users, because you all want to use your calculators. Whenever I start saying later on, hey, I need to take the area under this curve so we can find out the probability. And then your calculator is only going to give you this, but you need this. Well, can't you just take this and then subtract that from 1 to get this? Notice the complement. It's going to help out. A lot of really easy math is going to be done that way. Sometimes you might have to push a button on your calculator, but put in the word or put in the numbers 1 minus whatever number. Okay? You'll see shortly, don't worry. But I want you to kind of remember this whenever later on I start saying complement. I go, hey, what's the complement? You go, duh, it makes a lot more sense now. Okay? What is the probability of rolling a pair of standard 6-sided dice and neither dice is a 3? Now, the sample space of rolling 2 dice is this. Think about it. All the possible rolls in one is what? Six. We're rolling two dice. Close, you gotta think about it. No, because I could have a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1. So there's a lot. Okay, there's actually 36 different things you'd have to look for, and you gotta find each way, okay, what does it say here? That neither is a 3. Or maybe it's easier to find how many actually are 3s. Let me show you a picture. There's all the possible ways you could get a 3 right there. There's the sample space. Now, I just gave you the outcome space. Remember the outcomes or the universe we're looking at here is 36. So we know our number underneath is 36, right? Because of all the possible combinations I could get. So if I come in here and said, okay, if all this is 36, what is the probability of me, hear me out. What is the probability of actually getting a 3? That's what we're looking at now, right? What would be my top number? Get it carefully. Just literally count it. You're going to want to say 12, but it's not because there is somewhere they match.
Is it 9?
Close. Go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of 36. There is 11 out of 36 ways that I could get a 3, right? That makes sense how you see that? Is that what the question wants? No, it's saying what? How many ways is there not to get a 3? Well, remember, all these have to equal up to what? Yes, you're right, 36, but one, all probabilities, when you take the original probability and its complement, when you add them together, they have to get to 1. So to find what I'm looking for, I'm just gonna go 1 minus 11 over 36. Or, like Sabrina said, 36 over 36, simple math, right? So we just come in here and go 36 over 36 minus 11 over 36. Well, that gives us 25 out of 36. Notice this 25 here, that's what you would have had to find. 25 different data points. Okay, but instead I looked for the complement first and then just did some math and went back and it. Kind of see how it can be a little bit easier in a way? So, like I said, right here, the probability of not getting a 3 is equal to, right there, you can work out the decimal point on that one, okay? How to find the outcome space? I know I have 6 possible ways, and I put that at 2 because I'm using 2 dice. And so if I rolled dice once, pair dice, and then rolled dice again, remember that little question you had every trial? Remember for this one, you're having to go in multiples of 2 because you're rolling 2 dice every time. So it'd be 6 to the power of 2 for the first one, 6 to the power of 4 for the second one. Notice how much larger your sample is. Okay. For 2 events, E and F, the probability that E or F occurs is given by the following formula. The probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. Let's go ahead and dissect this a little bit so you kind of remember what this is. Let's go back in time. Does anybody remember what this is? When you saw that an OR symbol? Think of domains.
Union.
Very good. Who said union? Very good. Union, remember? When you have this or this, when you graph, you had to put that little U. Because in math, we don't have what we call an exclusive OR. Whenever I go tell my daughter, you can go do this or this. She can either do one or the other. But in math, when I say this or this, it's an inclusive OR. We combine things, okay? So that right there would be, it'd be, the union. We'll go and just put union right there. Well, what does and mean then? If one is a union, what's the other? What would be the, think about it. Has it been so long since college algebra? They didn't really hit sets too much in college algebra. I did, it took me, I hit sets really hard in intermediate. Think here, intersection. We got that kind of dissected. Let me show you what that means. I'm gonna give you a probability here. Let me show you something. Look at this. I give you a little Venn diagram because trust me, pictures will help you. My sample space, and then I have freshmen, I have math majors, okay? So we're gonna look at a probability here. What is the probability? Now, my sample space is going to be a university. Some generic, we'll use the JC. We could do this because it is freshmen, though we don't specifically have math majors. Okay, someone can say, I want to be a math major and just say you're getting associates of science, but we'll say math majors for right now. So my sample space would be all of the NMJC students, okay? And then we're gonna say this. I want to find the probability, so let's do this, an example here. The probability of, and remember when we're writing probabilities, we always put that little P, but then you can write a sentence if you want. You don't have to put little math symbols, you can actually write a whole sentence if you'd like. I want to say, what is the probability of me choosing randomly a math major or a freshman? And we're going to say this. I got to give you some numbers because it wouldn't work if I don't, right? So we're going to say 20% of the students on the JC campus are freshmen. Out of those freshmen, trust me, this number is very, very high. 0. Let's just do percent, sorry. Easier to just do this. 3% are math majors. So far, so good. Okay. And then I'm going to say this 0.5%. We're going to say, and it's maybe, we're going to say they're both. That means they're freshmen and they're math majors. Okay. So, why do I have this right here? Thinking of the graph right here. Could I find some freshmen? There's going to be a certain number of freshmen, right? I know there is. I have it up there for you. 20% of people could possibly be a freshman. How many of those people are math majors? 3%. So I have a whole nother number over here, right? Is it possible for there to be both? Obviously. When there's a possibility of both happening, that little intersection there, you have to subtract that out, or else people are getting counted twice. And so that part needs to go away, okay? You'll learn why that happens. We're going to learn a word here shortly called mutually exclusive. These are not mutually exclusive events. They could happen at the same time. Someone could be a math major and be a freshman, and I want to make sure I don't count them twice in my probability. Okay, and so you have to subtract them out. So literally the math to this, converting everything over to a decimal, is going to be 0.20 plus 0.03 minus 0.005. That's going to give me 0.225 or 22.5%. What this is saying, because remember, concept is key in this class. Yes, I show you math, but I want you to actually know something when you walk out of here. If I decided to just randomly walk around the campus and every single person was on the campus, or I did a random search, the chance of me picking someone who is a freshman, okay, or a math major is 22.5%. Okay, that's my odds. Not great odds. It's not a coin flip. Remember, coin flips are close to 50%. Okay, that kind of makes sense why that works. While we have to get rid of that in between. Okay? Hopefully you're kind of seeing, you gotta remove the overlap. Let's do this example here. Notice, Sarisa is looking for a new condo to rent. Sarisa's realtor has provided her with the following list of amenities for 17 available properties. Notice they give us all the probable outcomes. That's pretty nice of them when they do that. Okay? The list contains the following. Close to the subway, low maintenance, green space, newly renovated, close to the subway and low maintenance, green space and newly renovated. Okay? If Teresa's realtor selects the first condo they visit at random, what is the probability that the property is either close to the subway or has a low maintenance fee? Well, let's look at, we're looking for some probabilities. We've got the probability of, we're just gonna go and say E. Well, we'll say this right here. The probability is close to the subway. That'll be our E. So that'll be the probability of E right there. Well, what's that? Close to the subway? Looks to me like it's gonna be 6 out of 17 because look what it says right there. Gives me some numbers, doesn't it? So how about that one, 6 out of 17? The operative word I'm looking for that I hope you remember now, maybe for a midterm, is how do I know when I'm gonna use the addition rule? Or. Look for the or. Or says you're gonna use addition, okay? Or, which means I can add this in because it's an inclusive or, it's a union, or has a low maintenance fee. Okay, well, where else could that be? That's right here. Let's call that our probability of F, or just basically our F event. That looks right here. Well, that looks to be what? How about 7 out of, I put it 17 or something. 7 out of 17. Do you see anywhere that it might be both? Yeah. Look right here. That means those two are probably could also be found in the others up above. So when I'm looking for this probability, remember the rule, it's the probability of E plus the probability of F minus, okay, the probability of E and F. Where do they intersect? This right here would be the probability of E and F. So we can do this as 7 over 17 plus 6 over 17 minus 2 over 17. When we finish that off, we get 11 over 17 or 0.6471, which we know multiply that by 100 gives us a 64.71% chance that that's what we're looking for. But let me ask you this. What's the complement? How would you find that? What is the complement of this? Wouldn't it be everything that we're not looking for? Because what are we looking for right now? We're looking for what? An apartment that is close to the subway, low maintenance fees. The complement is everything else you don't want. Okay, and you would just subtract this number from 1, which will be 100%, right? Sometimes that's the question you need to ask. I get what the probability is of what I want, but what's the probability of getting what I don't want? Which in this case is pretty good. Hey, the probability of her getting what she doesn't want, only about what, 35%? That's not horrible. Okay, could be worse. You know, I might want to be less picky if I start looking at the complement being like 98%, like there's a 98% chance you're going to get what you don't want. Maybe I need to quit being so picky on where I live. I don't know. What we got here? But just a little bit, let's go one more. Now, we'll finish up with here today. I want to show you this. And it's pretty much, I mean, literally, it'll be pretty much after this, I'll have to do one little thing. When you have something that's called mutually exclusive, you don't have to get rid of the intersection. You know why? It's impossible to have one. Mutually exclusive events are events that cannot happen together. That's like flipping a coin. Is there a way for me to get a heads and a tails? That makes no sense. No, those would be mutually exclusive events. Okay, so the Venn diagram would not even be, there would be no intersection at all. So in this case, you would literally just add the events together. So what would be the probability of me getting a heads or another heads? Well, you would literally just do 1/2 plus 1/2. Okay? You just add the events together. Okay? It's sometimes kind of hard to see when something with classical math, it's kind of easy to see, but sometimes it's hard. Okay, like can it be sunny and cloudy? No, really not, but it depends. Or sunny and raining. They might, in some stat books, they'll say, no, those are mutually exclusive events, and yet I have been in the city where it has been raining and it's been sunny at the same time, so it just all depends. So you gotta kind of be careful about that kind of stuff. But some mutually exclusive events are very obvious, like can you roll an even number and get odd? No, those are mutually exclusive. They can't happen together. Okay, so if you're gonna take away anything from 4.2, I'll go through a few examples when we come back. We've only got about 3 minutes left. When we come back to class on Thursday, I'll go over a couple more examples in 4.2. We'll get into 4.3, 4.2, 4.1 and 4.2 is all that's due this week. Okay? But I want you to start being very aware of the and the or. In the next class, we're going about and. Okay? Now remember, when you're looking on your midterm, you're gonna want to know this. How do you know which one to use? What is the telltale sign of something you need to know of which probability I'm asking you for? Or when you see the probability of this or this, and it's gonna be flat out. I'm not gonna be like changing order. It'll be this or this. Then you have to go, okay, I'm doing the addition property. Then you have to go, is it mutually exclusive? Can these things happen at the same time? It's gonna be kind of, you're gonna know. Okay, good. All right, guys, see you later.